Good afternoon, ladies and gentlemen. This is the last session of this conference, and we have not very many talks online or offline. And Shobhan Chattopadhyay, I'm asked you to use the time. We discuss more about Tapan Nayak to deliver his talk. Tapan.
It's good to be back here after a gap of some years, and the past in-person meeting after the so-called pandemic. And thank you so much, sir, for giving me the opportunity to be here today. And especially, it has so happened that I am in the last session, so, which is also good for your turn. So today I am going to talk about thermodynamics of the little bang. So I will go over what is thermodynamics, and before that let me just for the students what is little bang. You will all know about the Big Bang. The Big Bang starting here 13.7 billion years ago, and it expands very fast, expanded very fast, very quickly, and now we are here at this point. So this Big Bang conditions we are going to recreate in the laboratory. I will go over it more in subsequent slides. And that we call little bang, because we can mark the Big Bang again. So the little bang is a heavy ion collision, collisions of iron and iron, lead on lead, gold on gold, even now proton on proton. You can hear me now? Better, okay. So, yeah, I don't have to look at that, my slide, yeah. Okay. So, so this is the little bang, which is the iron-ion collision, which we create in the laboratory. So this is what I'm going to talk about, the thermodynamics of the little bang. So what is thermodynamics? So thermodynamics, you all know, all of you, thermodynamics know better than me, the students who are here from different places. So thermodynamics deals with the study of energy, conservation of energy, and so on and so forth. And there are different laws of thermodynamics, which you can pick up in any textbook. Zeroth law, first law, second law. I don't want to go through, but some of the laws will be important as I go on, as I describe things. So I will give a little more emphasis on the zeroth law of thermodynamics, which is if the two systems are in thermal equilibrium with the third system, then they are in equilibrium with each other. That means A is in equilibrium with B, B is in equilibrium with C, so A is in equilibrium with C. So when I joined BECC 1996 December, so this thermodynamics actually helped me to a great extent. Professor Vikas Sinha is in thermodynamics with huge number of people. You can't even imagine the spectrum he has. And based on the thermodynamics zeroth law, I could also think that they are also my friends and go unhindered any places I wanted to. So, but you will get a glimpse of that. Oh, that's something came in between. This little bang we produced in collisions of relatively heavy collider at the large hadron collider at CERN. These collisions create systems of hot and dense matter similar to the Big Bang. So this is the topic I'm going to talk about. And before that, let me go over the zeroth law of thermodynamics. So first, you see, Professor Sinha, you know, our former president, Pranab Mukherjee. So this is a photograph from 2014 or 15. These are with the president, and president was really his friend also. So there are a lot of stories you hear from many people, even at CERN, how even Rudiger Voss, who was the director of international affairs at CERN, came with the president's flight from northeastern part of the country to Delhi. So this could be organized only because of Professor Sinha's influence in different places. And he is also at ease with the West Bengal Chief Minister, which he got the award yesterday. So there is no barrier of anything, no religion, no politics, nothing. It's just, the main thing is science. He wants to promote science and science administration, which he did for many years. He wants to promote that. So this is, you see a glimpse of that. Now, close friends in the right places. Here, you see Hans Gudbrand, who is not here, and is one of his closest friends. So along with Hans' collaboration, support, and with many of us, many at that time, Professor Sinha, Jürgen is here, and Federico, and Professor Sinha could start up the group. And when I was joining in '96, it was just at the beginning. It was already started long time back, but the Star and Arliss were just starting. So I was very lucky to be in that situation. You see Raphael, who gave a talk yesterday. You see Larry McLaren also who gave a talk. Many of you may or may not know Abdul Salam, the Nobel Prize winner. And you see, there are many pictures which I have. If you are interested, I can show you. So it is perfect thermodynamics with the little bang or the big bang, as you like. And also guiding us on the way. This is a photograph at CERN from the photon multiplicity detector of the Alice experiment just before it was installed. And our group is here from many different places, not from Calcutta, not only from Calcutta, but all over India. Muon arm, which is made in Saha Institute and Aligarh Muslim University. And this is a photograph in our K500 cyclotron at VCC. There are many such instances. He is always there with us whenever we need it and guiding us all the way in a thermodynamic manner. And often facing the media. He's always in the news, either in the print media or the television media or the radio, or in all over. So I could find this India on the moon when the Chandrayaan was landing. It was a very interesting interview. It is in YouTube, if you like, in Republic TV. And you see, in different media channels, he's always making news. And sometimes it's controversial. He says against the policies, and he says we should do this way, that way, and that actually helps, in overall scientific environment with us. And in harmony, and you can see this is a picture from Quad Party 2008 in Jaipur, and during the banquet we had a fantastic time with the dancing and the music and all that. So in perfect harmony with and in perfect thermodynamics with the surroundings and the all around. So with this small introduction, let me get to the thermodynamics of the little bang. So this Professor Subi Sakkar showed these cosmic microwave background pictures in the morning and analyzed in great detail in his talk. And these are the astronomical probes which are done by telescopes, many different probes which Professor Sakkar talked about, and the James Webb Space Telescope is new. These probes, and they probe different parts of the time frame in the Big Bang. So this cosmic microwave background, and this is a picture of the sky, picture of the infant universe taken by WMAP data. You have the temperature fluctuations. If you look at, these are temperature map at different theta phi points, and these are analyzed in great detail to get a lot of physics out, which he talked in the morning. And this astronomical probes actually we take us back to about the CMB when it is the temperature frozen almost. It is 380,000 years from the beginning. And we would like in the little bang or the heavy collisions, we would like to go beyond that. We want to go very close to the Big Bang, millions of a second, or even less. So the history of the universe is another picture of the Big Bang. If you look at the Big Bang till here, and you have astronomical probes which takes us to CMB, but the observation from here, one could go back all the way to Big Bang. But we would like to create in our accelerators, Large Hadron Collider or ring, we would like to create conditions which are very close to the Big Bang. If you look at the time slices, the nuclei are formed here within a few microseconds after the Big Bang. The quark-gluon plasma is actually a few microseconds. This is a little later than that. The nucleons, and then the nuclei, then the many things happen after that. So the proton-proton collisions takes us back little. After the Big Bang, 10 to the minus 20 or minus 30 seconds, and the heavy ion collisions, quark-gluon plasma is about a microsecond, if you like. So using the accelerators like Large Hadron Collider, we can probe systems which existed around that time. We can create conditions which existed around that time. So how do you know what kind of conditions existed at that time? So these are done, I'll come back to that. These are done by theoretical calculations. There are a lot of theoretical calculations going on for last several decades. And this is a calculation done from lattice calculations. Lattice is very sophisticated, time-consuming calculations. They make these calculations of temperature versus different parameters: energy density, velocity of sound, pressure, energy density, entropy density as a function of temperature. So we have they predict a phase transition temperature, and beyond that there is a quark-gluon plasma. Below that it's a phase transition. So this temperature is called a transition temperature. So they plot many different things. So in simple form, if you look at the energy density, it's a g pi square by 30 t to the 4. The g is the degrees of freedom. So in the hadronic matter, you have pions which are g equal to 3. But in quark-gluon plasma, number of degrees of freedom increases by order of 10, up to 37, 35, 40, like that. So we have gluons, different types of gluons, gluons, quark-Kreber, spin, all that. So this energy density, if you look at as a function of temperature, if there is a hadron gas, you will see some energy density which is g equal to 3, corresponds to g equal to 3. But if it is quark-gluon plasma, it will increase by about factor 10. So this is what is shown here. So theoretically, they get a transition temperature of 154 MeV. I am showing this because I will come back to the temperature. And energy density is about 10 times the normal nuclear matter density. Normal nuclear matter density, those who have nuclear physics, is quite high. So 10 times of that is shown is in the quark-gluon plasma. So these we calculate many hydrodynamic calculations, lattice calculations. They give all this type of result. And using that, we make a phases of the nuclear matter, different phases, temperature versus density. So you have a line which is the quark-gluon plasma. Beyond that, below this line is the hadronic gas. You have the Large Hadron Collider looking at the very high temperature, low baryon density matter. The relatively stable collider looking at the critical point. It's similar to the critical point or triple point of water. No time to go over. The FAIR facility coming up in Germany, who will scan the high density, high baryon density matter, hopefully to something which we will listen this morning. So this is a typical phase of the nuclear matter, and beyond this side is neutron star, quark-gluonic matter, which Larry McLean talked about, and all that. So the idea to understand the physics in terms of thermodynamics for me today. And this picture was shown by many people in Vedanga yesterday. The collision, when the layer of gold ions, they move at the speed of light, close to the speed of light, they are contracted, Lorentz contracted, they look like pancakes. So lead is a spherical nucleus moving at the speed of light, it looks like a pancake. They collide. After the collision, this is the collision point, the time t equal to 0. This is time where we measure. The measurement is mostly here. It's called freeze out. I'll talk about freeze out more. And in between, many things happen. After the collision, you have the quark-gluon plasma phase. You have then it goes to a hadronic phase. Then we have some measurement, and this is what we are trying to understand. So, initial state fluctuations. This is one of the important things. How to address the fluctuations which happen in the beginning of the collision. Then the thermal fluctuations. Then becomes hadronization. The quarks hadronize. Then come to the measurement of spectra, fluctuation, correlation. So I specialize in the fluctuation and correlation topics. So I will show some of the examples. The Large Hadron Collider, this is just a mandatory slide to show because this is where we take data, and you have this is a view from the top. You see the airport here. Geneva Airport, and this is 27-kilometer tunnel, underground tunnel. So two lead ions collide, or two proton-proton collisions happen at 4 different places. Point 1 Atlas, point 2 Alice, point 5 CMS, point 8 LHCb, 4 places. Atlas and CMS specialized for Higgs boson. They discovered Higgs boson, and they are going much more beyond that, symmetric, supersymmetric particles and all that. LHCb is looking for symmetry, asymmetry, beauty, physics. Alice is looking at the quark-gluon plasma. Okay, so this is how the experiments are set up. All experiments take heavy ion data. So I will combine, at the rest of my talk, I'll combine with the data from the relativistic heavy ion collider and Alice experiment. So first thing is thermodynamics. Now many of you must be thinking, you are only colliding lead on lead or gold on gold. You are producing only small number of particles. Can you apply thermodynamics? So yes, there has been a lot of success story of applicability of thermodynamics. And this is a display of the proton-proton collision at 13 TeV at LHC, the highest energy so far. Proton-lead collision, lead-lead collision. And if you have good eyes from the back, you can see this event display. That means you will see the lines coming out. The lines, each line is one particle. So the number of lines you will see going up from here to here to here. Here we may have typically few tens, 10, 20, 30 up to 100 particles, maybe, yeah, in the central. This may be few hundred, but here we have about 2,000-3,000 particles we measure. So if you, from the measurement, if you make a plot of number of particles as a function of centrality which is like the collision which is head-on collision is central. If you have a grazing collision, it is a peripheral collision. So as a head-on collision, you produce more particles. So this side is head-on collision, central collision, this side is peripheral collision. The number of particles are going up as a function of centrality. But you look at the volume, these are the volume is different type of radii, radius in 3 different dimensions. You will see that also increases. So the number of particles are increasing, the volume is increasing. So we can say that the growth, there is a nice growth in the number of produced particles as well as the volume. So as a function of centrality and collision energy, N by V, the number by volume, remains more or less constant. So this is one of the validity of the thermodynamics. Second one, the hydrodynamic calculations. We talked about hydrodynamic calculations for last few days here. There is a nice, good success of hydrodynamic calculations in explaining low momentum physics data. So that also, these two gives us confidence that we can apply thermodynamics to get what you want to do. There's a temperature, pressure, and all that. Now, just before I move on, this is the slide, so in a different version, so it was shown by Federico, Professor Sinha, Srivastava, Dana Alam, and the group from here. The expertise on the photons, direct photon signatures. The photons which come out of the collision, they are photons from the different processes, physics processes, plus photons coming from pi 0, the neutral pi. So they dominate. So the extraction of this data is extremely difficult. So now I didn't put the new data which Federico showed. I had the data from 2.76 TeV, and if you look at, this is from Phoenix, from RIG. This data is from our data from LHC Alice, and we get a temperature which is 297 with some error bar MeV. This temperature is from the direct photon. That means photons which get produced early in the collision, they pass through everything, and then we measure at some point. They are called effective temperature. They have a memory from beginning to the end. So it's not really initial. In the calculations which Professor Sinha Srivastava put, they can really take an initial temperature and do the calculations and explain the data. So this temperature, if you compare to the temperature of the core of the sun, it's about 100,000 to 200,000 more than that. So this temperature at the core of the sun is 27 million degrees Celsius, and we get a temperature 3 million, 10 to the power 12 degrees Celsius. So this is one way to get the temperature, which is first thing to look at the thermodynamics. So I will now go to 2 different temperatures. This is a temperature, effective temperature from photon spectra. I will go to 2 different temperatures, which I will define subsequently. This was shown by Federico the first day, and the evidence for production of thermal systems. We normally make spectra. Spectra, when you have everything is called spectra. This is momentum on the x-axis, y-axis the cross section, and you have beautiful data of ions which are coming out, kaons and protons. They make really nice spectrum. We have a central and peripheral. By making a nice fitting to this, it's called a Boltzmann-Gibbs Pascoe model fit, and which introduces a temperature plus a radial flow, and the particles are moving out, flowing out, so you have flow velocity. Introducing these two, we get a temperature, and we can write down a cross-section equation, and then using that, we get a kinetic temperature, call it a kinetic temperature. This is the temperature at the end of everything. We measure at the end of everything frozen out, it's called kinetic temperature. We get a radial flow boost. So temperature and radial flow, they give a very nice distribution like this. They can scale properly. So using this one, we can try to find out also the number of degrees of freedom. I'll just show you in few slides. The second thing is evidence of production of thermal system. Number two, if you look at the number of particle production and then feed with a statistical Boltzmann, simple Boltzmann model, and these are pions, kaons, like the protons, all particles, and just feed how they can be reproduced using a Boltzmann function, simple abundant, simple cross-section, d and dy is proportional to minus m by temperature. This temperature is called a chemical temperature, where the particle production stops, like there is no production anymore, they are just going through different processes to get the, so this is called chemical temperature, the other is called kinetic temperature. This temperature is slightly higher. This temperature is 153 MeV. The temperature from here is about 120 or 100 or 100 MeV for central collision. So kinetic temperature is after, chemical temperature is before. So I have used three temperatures from the direct photons. This is the kinetic temperature, then the chemical temperature here. It's about 153 MeV. Now, the lattice calculations also are extremely powerful for predicting different thermodynamic susceptibilities. Like also from there we can extract temperature. So what one does, we from our measurement we can try to find out positive particles, negative particles, positive ions, negative ions, make their distribution as a constant centrality, fit how they look like, the mean, sigma, skewness and kurtosis. So this mean, sigma, skewness, kurtosis, from there lattice calculation, if you combine, we get a temperature of chemical result temperature of 150 MeV. That both two different methods, completely different independent methods, they match quite well, and there are a lot of work going on still, but they, in the first order, they match. So this is another good success of lattice and also of thermodynamic understanding. Now, let me move on to another two important things which we recently did, and here, I think, first